File system backups. While the file system cannot offer any protection against physical destruction of the equipment and media, it can help protect the information. Make backups. It is not quite as trivial as it sounds. Backups to tape or to other devices are generally made to handle one of the two potential problems. 1. Recover from disaster. 2. Recover from stupidity. Notice that tapes hold hundreds of gigabytes and are very cheap. Making a backup takes a long time and occupies a large amount of space, so do it efficiently. First, should the entire file system be backed up or only part of it? It is usually desirable to back up only specific directories and everything in them rather than the entire file system. Second, it is wasteful to back up files that have not changed since the previous backup. So, incremental dump is used, but it complicates recovery. Since immense amount of data are typically dumped, that is put in mass, it may be desirable to compress the data before writing them to tape. This decreases reliability. It is difficult to perform a backup on an active file system. It may generate inconsistency. And the last one is making backups introduces many non-technical problems into an organization. Offsite storage, security issues, etc. Two strategies for dumping a disk to a backup disk are physical dump or logical dump. A physical dump starts at block 0 of the disk, writes all the disk blocks onto the output disk in order, and stops when it has copied the last one. In this case, unused blocks and bad blocks should be handled properly. The advantages are simplicity and speed. Disadvantages are inability to skip selected directories, make incremental dumps, and restore individual files upon request. A logical dump starts at one or more specified directories and recursively dumps all files and directories found there that have changed since some given base date. Example algorithm dumps all directories, even unmodified ones, that lie on the path to a modified file or directory for two reasons. The first one is to make it possible to restore the dumped files and directories to a fresh file system on a different computer. The second one is to make it possible to incrementally restore a single file, possibly to handle recovery from stupidity. In this figure, a file system to be dumped is given. The squares are directories and circles are files. The shaded items have been modified since the last dump. Each directory and file is labeled by its inode number. Here notice that the files 3, 8, 9, 17, 21, 24, and 26 are changed. And also the content of the directories 16, 20, and 22 are changed. The content of a directory may be changed because of a subdirectory or a file is added or deleted. In taking system backups, in phase 1, mark each modified directory and file. Phase 2, unmark directories that have no modified files or directories in them or under them. For example, 10, 11, 14, 27, 29, and 30 in the example. Phase 3, scan inodes in numerical order and dump all the directories that are marked for dumping prefixed by their attributes. Phase 4, dump the files marked prefixed by their attributes. For this directory, given the files and directories changed, the result of the bitmap at the end of phase 1 is such that all the inodes are marked except for the files which are not modified. The files which are not modified are 4, 12, 13, 15, 25, 28, 31, and 32. Then those directories which are not modified and having only not modified files are unmarked. So the directory 10, 15, 14, and also 28, 29, and 30 are unmarked in this way. Then in step 3, the files which are modified are backed up. Which are the files? 3 at 9, 17, 21, 24, and 26. These are the files modified. After they are backed up, they are marked as unmodified. And after that, in step 4, those directories which are marked are backed up and they are unmarked in the bitmap. And so the file backup is completed. The issues in restoring a logical dump are: restore free blocks list, restore linked files only once, do not restore holes in Unix files, do not dump and restore special files such as pipes. File system consistency. Many file systems read blocks, modify them, and write them out later. If the system crashes before all the modified blocks have been written out, the file system can be left in an inconsistent state. This problem is especially critical if some of the blocks that have not been written out are inode blocks, directory blocks, or blocks containing the free list. Hence run the utility fsck file system check in Unix or sfc system file checker in Windows, especially after crash. Consistency check can be done for block consistency and file consistency. These are the counters keeping track of how many times each block is presented in a file, while the values here are the counters keeping track of how many times each block is present in free list. This mapping is corresponding to a consistent file system. Notice that when the value is 1 for the blocks in use, it is 0 for the free blocks. In part B, the case a block is missing is shown. For the block 2, the value is 0 both for blocks in use and free block, which should be either one here or here. Part C shows a duplicate block. Notice that the value is 2 here. That means that this block is shown 2 times in the free list. And here, a case for the duplicate data block is given. The value is 2 here, showing that that block is used 2 times in the files. And these 3 cases are corresponding to inconsistent file systems. File system performance. While reading a 32-bit, memory words take about 10 nanoseconds at 400 megabytes per second speed. Disk word takes approximately 40 nanosecond at 100 megabyte per second, but after 5 to 10 millisecond seek time. Hence, million times slower when a single word is to be accessed. Many file systems have been designed with various optimizations to improve the performance. Caching, block read ahead, and disk arm motion reduction are possible techniques to be used. Caching is one of the approach. A buffer cache is a collection of blocks that logically belong on the disk but are being kept in memory for performance reasons. This is shown the buffer cache or block cache data structures. We have a hash table. Each entry in the hash table is a pointer to a linked list.
Note.
And this linked list is showing, and this linked list has in front the least recently used block, and the element at rear is showing most recently used. Many, often thousands of blocks in the cache, hence some way is needed to determine quickly if a given block is present. Hash the device and disk addresses and look up the result in a hash table. All the blocks with the same hash value are chained together on a linked list so that the collision chain can be followed. When cache is full, some block has to be removed. This is very much like paging and all the usual page replacement algorithms, first in, first out, least recently used, etc. are applicable. Now, exact least recently used is possible, but it may be undesirable due to increased inconsistency probability. Some blocks are rarely referred 2 times within a short interval, leads to a modified least recently used scheme taking 2 factors into account. 1. Is the block likely to be needed again soon? 2. Is the block essential to the consistency of the file system? To increase the file system performance, read ahead is another choice. It is used to increase the hit rate. It gets blocks into the cache before they are needed. When file system is asked to read block K in a file, it does that, but when finished, it makes a sneaky check in the cache to see if block K+1 is already there. If it is not, it schedules a read for block K+1 in the hope that when it is needed, it will have already arrived in the cache. Of course, this strategy works only for files that are actually being read sequentially. Another way to increase the file system performance is reducing disk arm motion. Reduce the amount of disk arm motion by putting blocks that are likely to be accessed in sequence close to each other, preferably in the same cylinder. When an output file is written, the file system has to allocate the blocks one at a time on demand. If the free blocks are recorded in a bitmap and the whole bitmap is in main memory, it is easy to choose a free block as close as possible to the previous block. With a free list, part of which is on disk, it is much harder to allocate blocks close together. Another performance bottleneck in systems that use inodes or anything like them is that reading even a short file requires 2 disk accesses, one for the inode and one for the block. In usual inode placement, all the inodes are near the start of the disk, so the average distance between an inode and its block is half the number of cylinders, requiring long sieves. Part A in this figure is showing inodes placed at the start of the disk. Inodes are located near the start of the disk. So when a block is to be accessed, first the track containing the inode should be accessed and then the actual block of the data. And this slows down the operation. Here in part B, disk is divided into cylinder groups, each with its inodes. Here, these are the cylinders reserved for the inodes. Here in the structure, inodes are close to the actual blocks of the file, so the time required for disk arm motion is reduced. Disk arm movement and rotation time are not issues related to solid-state disks, SSD, which have no moving parts whatsoever. For these disks, built on the same technology as flash cards, random access are just as fast as sequential ones. But in SSDs, each block can be written only a limited number of times, so great care is taken to spread the wear on the disk evenly.